Okay, let's dive in. When you hear Einstein, when you hear relativity, what pops into your head?
Probably something brilliant, definitely game-changing.
Right. But maybe also a little bit, I don't know, intimidating. Like it's all wrapped up in complicated math.
Yeah, that's often the feeling. You know it's important, super profound, but the actual ideas can feel kind of hidden behind the equations.
Exactly. And you want to get it, you want to feel like you understand the big picture without needing a PhD in physics, right?
Hmm.
Well, that's exactly what we're aiming for in this deep dive. We're going to explore the core, really mind-bending concepts of relativity based on the sources you've provided.
Yeah, the goal here is to pull out the most crucial insights, the real nuggets from this material. Give you that imaginative feel for the shift in thinking, not just the formulas.
Perfect. And our source material kicks things off with this really great contrast. Think about how we usually experience the world just day to day.
Yeah.
We use touch, we use sight. You know, we measure things with rulers, maybe pace things out. We judge distance by looking, but we often trust touch for what feels real. Like a good argument feels solid, right? A weak one feels like hot air or gas.
That tactile sense, yeah, it's fundamental for us on Earth. But then you look at astronomers.
Right. They only have sight. They can't touch the stars, can't lay a ruler across the solar system.
And for a long time, they just sort of took our Earth-based, touch-based physics and geometry and tried to stretch it across the whole universe.
Which, as our source points out, led to some serious problems. Einstein had to clean that up, basically showing that a lot of what felt solid from touch was just, well, prejudice from a bigger perspective.
There's this brilliant analogy in the source to help us shed that prejudice. Imagine you're a drug balloonist.
Okay.
You wake up high above the ground, pitch black night. Maybe there's a huge fireworks show going off below. You've got amnesia, can't see the ground, no landmarks, just these flashes of light.
Wow, okay. So my whole world is just these weird, fleeting points of light zipping around, no stability.
Exactly. Nothing permanent, nothing solid you could ever touch. And if someone tried to tell you about fixed ground or walking distance, it would sound totally bonkers.
I can see that.
But here's the twist. The source suggests if Einstein was there with you, his ideas about reality being relative and changing might actually seem easier to grasp, because you wouldn't have those ingrained Earth-based assumptions weighing you down.
Huh. That's fascinating. So letting go of those assumptions is key. Because our normal life, with things staying put mostly, it builds these ideas of absolute space, absolute time.
Ideas that feel necessary, but are really just, very good approximations for our scale.
Like taking a train journey, say, London to Edinburgh. We say we travel to Edinburgh, we don't say Edinburgh is rushing towards us.
Right. And that only works because the stations, the tracks, the planet itself are all pretty much stationary relative to each other.
Which the source calls basically cosmic luck. Imagine if houses and roads moved like a swarm of bees.
The whole idea of being in a definite place would just dissolve.
It's a practical shortcut that works for us, living on this relatively stable rock.
But zoom out, and even the fixed stars are actually whizzing around like crazy. So deciding what's really moving in astronomy, the train or the station, it's just convention.
And if place and motion are approximate, what about force? That also comes from our bodies, right? Pushing, pulling.
Yeah, seems intuitive. But even Newton had that weird action at a distance problem with gravity. How does the sun just pull the Earth across empty space?
It was always a bit mysterious.
And Einstein found a way around needing that mysterious force. But it meant he had to fundamentally change our ideas about space and time themselves. Those things we thought were unquestionable.
Which brings us to this really vital distinction the source makes early on. The difference between what happens and what we observe.
Yeah, the classic example. A gun fires, you see the flash.
Then you hear the bang later.
Right. They happen together at the source, but sound is way slower than light, so distance makes you observe them separately.
Okay, light is incredibly fast, though. 300,000 kilometers a second, roughly.
Insanely fast.
Yeah.
So for things happening nearby on Earth, it feels instantaneous. See, it happened right then.
But light from the sun still takes, what, 8 minutes?
Yep. And light from stars. Years. Thousands of years sometimes.
And this finite speed of light becomes absolutely crucial when you look at really fast things like electrons.
Exactly. Electrons moving near light speed. Old physics couldn't predict how they behaved. Experiments showed really weird stuff.
Weird like how?
Well, for starters, their mass seemed to increase the faster they went.
Wait, mass increases with speed? That's odd.
Gets weirder. Their size seemed to change too. They appeared to get shorter, squashed in the direction they were moving, but only from the perspective of someone not moving with them.
So if I flew past you near light speed holding a ruler, you'd measure it as shorter.
That's the idea, and maybe the craziest part. Time itself gets warped by motion. If you had two perfect clocks, sent one on a super fast trip and back, they wouldn't agree on how much time had passed when you compared them.
Hold on. Is this just like the gunshot, like delays in seeing things because light takes time? Or is it real?
That's the million-dollar question. And the source is clear. No, it's not just observational delays or illusions. These are described as genuine physical differences.
Wow.
An observer moving with the electron measures time and space differently than an observer on Earth measures for that same electron, even after they both account for light speed delays. Their relative motion genuinely changes the physical measurements.
So reality itself is different depending on how you're moving relative to what you're measuring.
That's the unavoidable conclusion. And the source notes that, interestingly, the reasoning behind this could have been figured out earlier, but it often takes those weird experimental results to force us to see that the old assumptions must be wrong.
Which leads us right into the principle of relativity.
Yeah, think about choosing a reference point for motion. The train, the Earth, the sun. You can pick any of them.
And describe everything else relative to that point.
Right. And doing that doesn't change the relationships between the other objects. It's like measuring wealth in dollars versus euros. The numbers change, but who's richer or poorer stays the same.
Yeah.
The absolute core idea, the generating motive, as the source puts it, behind relativity is this. The actual laws of physics must look the same, must work the same, no matter which uniformly moving observer is describing them.
So the rules of the universe don't suddenly change just because I'm on a fast train versus standing still.
Exactly. The laws have to be invariant. But if the laws stay the same, yet measurements of space and time do change depending on your motion.
Then space and time can't be the absolute objective things we thought they were.
Precisely. They must depend on the observer. What's left, what's truly objective, is only some kind of residue that belongs purely to the events themselves, independent of how anyone measures them.
And that objective residue is what the laws of physics are actually about.
Which is where space-time comes in. It's not space and time anymore, but this objective mixture.
Okay. And you said a lot of the weirdness comes down to the speed of light.
Yeah, its constant velocity is key, about 300,000 kilometers per second in a vacuum. We know this from things like observing Jupiter's moons.
Right. But the old idea was that light needed something to travel through this ether.
Like sound needs air. And if there's an ether, then the speed of light should be relative to the ether. So as the Earth moves through this ether...
You should be able to measure a difference in light speed depending on whether you're measuring with or against this ether wind.
Exactly. Like rowing a boat upstream versus across stream, the current affects your speed differently.
Which sets the stage for the Michelson-Morley experiment, a really famous, crucial experiment.
Absolutely critical. They built this incredibly sensitive device to split a beam of light, send it in two different directions at right angles, bounce it back, and recombine it. They were looking for that tiny difference in speed caused by the Earth moving through the ether.
And what did they find?
Nothing. Absolutely nothing. No difference at all.
Wait, nothing?
Zilch. The speed of light was the same in all directions relative to the Earth, and they tried it at different times of the year when the Earth's direction through space changes. Still nothing.
But how? If I run towards a flashlight, shouldn't the light seem to come at me faster?
That's what common sense says. But the experiment says no. And the wider implication, combined with other results, was even stranger. If you send out a light signal, the source of that light always stays at the center of the expanding sphere of light, no matter how the source itself is moving.
Okay, hold on. If I turn on a light and then run, the light doesn't spread out from where I turned it on. It spreads out centered on me, even as I'm moving.
According to the physics, this implies yes. The source uses a great analogy. A fly touches a still pond. Ripples spread from that spot. That's normal waves.
Yeah.
But if these were light ripples, and the fly was the source, the ripples would always be centered on the fly itself, even if it was buzzing across the pond.
That feels completely impossible.
It really does at first glance. But this impossible experimental result, the constant speed of light for everyone, was the key. It, along with those other weird effects like length contraction, forced Einstein to realize our basic assumptions about space and time had to go. That led to the special theory in 1905.
And one of the biggest casualties was absolute simultaneity. The idea that two things happening far apart could definitely be said to happen at the same time for everybody.
Jan, kaput.
Yeah.
Think about how you'd naturally judge simultaneity. The source suggests if you're standing exactly halfway between two events, say two firecrackers,
And you see the flashes at the exact same instant.
then you'd say they happen simultaneously, right?
Yeah.
Because the light took the same time to reach you from both. Makes sense.
Okay, yeah.
Now, back to the train. Two guns fire, one at the front, one at the back, simultaneous for someone on the ground halfway between them. But what about someone on the train also halfway between the guns on the train?
Uh-oh. The train is moving.
Right. So while the light is traveling towards the person on the train, they're moving towards the light from the front gun and away from the light from the back gun.
So the light from the front gets to them first, even though the person on the ground swears they fired at the same time.
Precisely. The observer on the train will not judge the events as simultaneous. And physics can't play favorites. We can't just say the Earth observer is right because we live here. A physicist on a speeding comet has an equally valid viewpoint.
So on a cosmic scale, someone whizzing past Earth really fast would disagree with us about whether an event on Earth and an event on Jupiter happened at the same time, even after they account for light travel time.
Yes. Simultaneity itself is relative. It depends on your motion.
Wow! Okay, so this also messes with our ideas of clocks and rulers.
Fundamentally, a clock is just any regular repeating process. The Earth spinning, atoms vibrating. Our watches just make it convenient to track.
And a clock measures its own time, its proper time.
Right, which is physically real and important. But that clock's reading doesn't directly tell you the time for events happening on things moving rapidly relative to it. You need more info.
And same for distance. A ruler measures length, but that length isn't absolute.
Nope. Think about the distance between you on the train and Edinburgh. It's constantly changing for you. Someone on the sun would measure it differently. Even a tiny flea on the train floor would have a different perspective on that distance.
And nobody's wrong.
According to the source, you're only wrong if you claim your measurement is the only objective truth. Space measurements are relative. Time measurements are relative.
So, is anything objective left between two different events?
Yes. And this is huge. You can combine the space separation and the time separation between two events to find one single quantity that is objective that all observers will agree on. This is the interval.
The space-time interval. This is the replacement for separate space and time.
It is. It's the objective reality underneath the relative measurements. The force outlines three types. First, a zero interval. Possible only if light can travel between the two events. One event is basically the seeing of the other.
Okay, connected by light.
Second, a space-like interval. The events are so far apart in space compared to the time between them that nothing, not even light, could travel from one to the other.
Too far, too fast.
Right. But crucially, for space-like separated events, it's always possible for some observer moving just right to judge them as happening simultaneously. The interval, in this case, is the distance that specific observer measures between them.
Interesting. So simultaneity is possible only for space-like events.
For some observer, yes. Third type, time-like interval. Here, the events are close enough in space relative to the time separation that a physical object could actually travel between them at less than light speed.
Like me traveling from London to Edinburgh.
Exactly. And the interval in this case is the time measured on the clock of the person or object actually making that journey between the two events. Your proper time.
Ah, so the interval is my own elapsed time if I can physically get between the events.
Precisely. That interval is objective. Everyone agrees on its value, even though they disagree on the separate space and time measurements that go into calculating it, using the formula from special relativity. It's this invariant interval that forms the bedrock.
Replacing two relative things, space and time, with one objective thing, the interval.
That's the heart of it. Which leads us to why we say space-time. It's not two separate stages anymore.
Right. We used to think 3 dimensions of space, up, down, left, right, forward, back, and one separate dimension of time.
Yeah. To pinpoint an event, like, say, an explosion somewhere, you need 4 numbers. Latitude, longitude, altitude, and the time it happened.
Traditionally, 3 space, 1 time.
But the killer point is, because space measurements are relative, 3 coordinates are not enough to objectively locate something anymore. You need all 4 together to specify an event in this unified 4-dimensional space-time. That's the swap. Space-time instead of space and time.
And this 4D space-time structure is what naturally explains those weird effects. Length contraction, time dilation, mass increase.
Yes, the math works out. The source mentions a geometric picture relating these effects to the ratio of the object's speed to light speed.
And they're reciprocal, right? If you fly past me, I see your clock run slow and you see my clock run slow.
Exactly, it's symmetrical. And these effects are tiny unless you get really close to light speed. But they were real, measured effects that pushed Einstein towards this new framework. The old way just didn't work because it assumed absolute simultaneity, which the constant speed of light killed.
So now you always need the when along with the where to talk about something objectively. An event in space-time. No universal now.
Okay, but all of that was the special theory of relativity. It only dealt with uniform motion, constant speed, straight line.
But most things aren't like that. Planets orbit, things fall. That's acceleration. Changing speed or direction.
And you feel acceleration, right? Slam on the brakes, take off in a plane. It feels different from smooth cruising. So relativity needed a bigger framework to include acceleration. That's the general theory.
And this is where it gets even weirder. Geometry becomes physics.
Pretty much. Think back to basic geometry. Euclidean geometry. Flat surfaces. Pythagoras' theorem for right triangles. Using x, y, z coordinates.
A squared plus b squared equals c squared.
Yeah, works perfectly on flat paper.
Yeah.
But try it on a sphere, like the Earth's surface. Draw a big triangle. The angles add up to more than 180 degrees.
Right, because it's curved?
And Pythagoras fails. The shortest path between 2 points isn't a Euclidean straight line anymore. It's a curve, a geodesic, like a great circle route for airplanes. Riemann generalized this, showing that the geometry of any space, curved or not, is determined by how you calculate tiny distances within it, a sort of localized Pythagorean theorem.
And Einstein applied this.
To space-time. He said, let's replace distance with the space-time interval we just talked about. Let's use 4 coordinates, 3 space, 1 time. And let's assume the geometry of space-time is described by a formula for this interval, which might vary from place to place.
Okay. So how does this relate to gravity? Newton's gravity was a force.
Yeah, an instantaneous force acting across absolute space based on absolute distance. But we just saw space, time, and simultaneity are relative. So Newton's law, based on those absolute concepts, just can't be fundamentally right in this new picture.
The logic breaks down.
Exactly. The laws of physics need to work regardless of how we arbitrarily label points in space-time with coordinates. It shouldn't matter if you use GPS coordinates or, directions relative to the nearest coffee shop.
Like the source's analogies of mapping on rubber or using a wriggling eel to measure, the relationships matter, not the absolute labels.
Right. Geometry itself has to be part of the physics. Coordinates are just bookkeeping.
So what is gravity in Einstein's general theory?
It's not a force anymore. It's the curvature of space-time itself.
Whoa.
The idea is matter and energy warp the fabric of space-time around them. They create curves, hills, valleys in this 4-dimensional geometry.
And things just follow the curves.
Basically, yes. The theory says objects, like planets and light rays, if they aren't being pushed by other forces, follow the straightest possible paths through this curved space-time. They follow the geodesics.
Like the shortest path on a curved surface?
Sort of. For objects with mass, the geodesic is actually the path that maximizes the proper time experienced by the object between 2 events. The time on its own clock. It's the path of least action, in a way. Light rays follow geodesics where the interval is 0.
So planets orbiting the sun aren't being pulled by a force. They're just following the straightest possible path through the curved space-time the sun creates.
That's the revolutionary idea. Gravity is the geometry. The feeling or appearance of a force only comes about because we're trying to describe motion in a curved space-time using our old flat space intuition.
Like the source's analogy of seeing lanterns move towards a beacon on a hill at night?
Yeah. From above, it looks like the beacon is pulling them. But in daylight, you see the hill and realize they're just following the natural contours, the easiest paths.
The sun is the beacon creating the hill in space-time.
Exactly. Its mass creates the curvature. Planets follow the geodesics on that curvature.
Mind blown. Okay, but this isn't just a nice story, right? There's evidence.
Oh, yeah. Crucial evidence. First, general relativity perfectly explained a tiny wobble, an anomaly in Mercury's orbit that Newton's theory just couldn't account for.
Okay, solved an old problem. What else?
The big one. Einstein predicted that light from distant stars passing close to the sun would be bent by its gravity by the curvature of space-time near the sun. He predicted a specific amount of bending, twice what a simpler Newtonian approach might suggest. In expeditions during a solar eclipse in 1919, measured the positions of stars near the sun, and they found the bending Einstein predicted.
That must have been huge news.
It was enormous.
Yeah.
Catapulted Einstein to worldwide fame. That light bending is now very well confirmed. There's also evidence for gravitational redshift light, losing energy as it climbs out of gravity well, shifting towards red, though it's harder to measure.
So, strong experimental backing,
Yeah.
plus the logical argument you mentioned.
Right. Relative motion plus constant light speed forces relative space-time, which breaks Newton's gravity law. You need laws that don't depend on arbitrary coordinates. And that weird fact that gravitational mass, what gravity pulls on, and an inertial mass, what resists acceleration, are always equal.
Why is that equality so important?
Because it strongly suggests gravity isn't like other forces. It seems to be linked directly to inertia and acceleration, which points towards a geometric explanation where acceleration and falling in gravity are fundamentally the same kind of motion following geodesics.
Okay, and relativity also changes how we think about mass itself.
Yeah, we saw measured mass increases with speed. But there's also proper mass, the mass measured when you're moving with the object. That's seen as an intrinsic property.
But even that isn't always conserved, like in nuclear fusion.
Right. When hydrogen fuses into helium, a tiny bit of the proper mass disappears.
Where does it go?
It's converted into energy.
This
This leads directly to maybe the most famous equation ever, EMCK. Energy is mass, and mass is energy. They're interchangeable.
Wow.
The old ideas of separately conserving mass and energy are just approximations that work well at low speeds. Fundamentally, it's mass energy that's conserved, along with momentum, in a unified way.
And this changes our picture of matter, too, not solid stuff anymore.
The old view of persistent substance was tied to absolute space and time. That's gone. The new view, according to the source, sees the physical world built from things as limited in space-time as possible. Basically, events.
Events, like happen.
Yeah. Think of fields, waves, interactions occurring at points in space-time. Even empty space has fields, and light waves passing through those are events. Matter, like an electron or proton, is seen as a region where the simple laws of how these waves or disturbances travel break down, a sort of localized knot or stable pattern of events or disturbances.
So an electron isn't a tiny ball, but more like a persistent disturbance pattern in fields.
That's a way to think about it. The source uses the analogy. You don't see the substance of a table. You see light bouncing off it, causing events in your eyes and brain. Similarly, we know an electron by its effects, the fields and disturbances it creates. Physics describes those effects.
And the source suggests maybe the effects are the electron, or at least that's all physics can confidently talk about.
Exactly. Avoid adding extra layers like substance if the physics works by just describing the pattern of events. It doesn't change the math, but it changes the philosophical interpretation of what the math represents. And the math is usually more solid than the interpretation.
Okay, stepping back then. Philosophically, this subjectivity and relativity measurements, depending on the observer, it's not just mental, right?
No, it's physical. Clocks really run differently. Lengths really measure differently depending on relative motion. But the beauty is, the theory also gives you the tool, the interval, to find out what is objective, what everyone agrees on.
But a big consequence seems to be that physics tells us less about the what of the world, the actual nature of things.
Yeah, maybe less about the stuff and more about the structure, the mathematical relationships between events. Old great principles like mass conservation turned out to be approximations or based on measurement conventions.
Physics becomes truisms and geography, mapping relationships in space-time.
In a way, distance isn't simple anymore except locally. Straight lines become geodesics. Even basic causation like A forces B gets replaced by A and B, both following the geometry of space-time.
And relative time could even mess with ideas like cosmic progress. Whether the universe is getting better might depend on whose clock you use.
That's a mind-bending implication the source mentions. It might seem to spoil the poetry, as it says. Our knowledge becomes very abstract. We know the mathematical laws governing occurrences, but maybe not their intrinsic nature.
But that abstraction is powerful.
Incredibly. Like a financier dealing with abstract markets gets real-world results, abstract physics gives us immense power to predict and manipulate the world.
And that idea of matter being events, the source calls it a minimum definition.
Yeah, like this much must be true if physics works. It doesn't rule out deeper layers. The source mentions Leibniz's idea of matter as colonies of souls. But science itself can't currently say anything about that, positive or negative. It sticks to what the evidence supports.
Okay, so let's try to wrap this up for you listening. We've journeyed through Einstein's relativity, starting by questioning those everyday ideas rooted in touch and stationary objects.
We saw how crucial experiments, especially light, always traveling at the same speed for everyone, shattered the foundations of absolute space, absolute time, and universal simultaneity.
We found that while space and time measurements are relative, this combined thing, the interval in space-time between events, is objective. That's the new bedrock, this four-dimensional space-time.
And then in general relativity, gravity itself gets reimagined. Not a force, but the curvature of spacetime caused by mass and energy. Objects and light just follow the straightest paths geodesics through this curved landscape.
A radical picture, but one backed up by solid evidence like Mercury's orbit and bent starlight.
We also saw matter and energy become fundamentally linked, EMCI Lux, and matter itself viewed less as stuff and more as localized patterns of events or disturbances in spacetime fields.
And the overall effect is that physics becomes more abstract, describing mathematical structure rather than intrinsic nature, turning old certainties into approximations.
It's a huge shift in perspective, asking us to abandon some really basic intuitions. But the understanding and power gained have been immense.
So, here's the final thought to leave you with. If our most successful description of physical reality tells us that space, time, and even simultaneity depend on how we move, and that the fundamental reality is described by abstract mathematical relationships, what does that really mean for the solid, tangible world you experience every day?
Yeah, how much of what feels obviously real is just a consequence of our specific, limited, earthbound perspective? What other bedrock assumptions might just be convenient approximations waiting for the next Einstein or the next crucial experiment to overturn? Something to chew on.